And, but the idea here is that we have this globe, right? As long as we didn't conquer the galaxy, our problem is this globe. And to cover this globe, at the time, we thought, we need about 1,000 nodes. So if we come up with protocols that can scale just to 1,000, not to millions of the internet, they're much smaller in that regard. I mean, they cover the whole globe, but they're small in that regard. Then they can have more information about each other. They can be tighter about each other, and then that gives you much better performance. You can do things you cannot do on the internet, and you're much smarter. You can be much smarter, not because you're smarter than the other guys, it's because you have more information, that's all. So that's the idea. How do you do it? You basically build a layer, those computers and those regular programs, you will see them in a few minutes, that sits on top of the internet. It's a much smaller network in terms of numbers, and every link on that network is really an internet path. And you need to come up, if you want to go from here to there, let's say from here, okay, to there, you say, okay, on the overlay I'm going like this. On the internet, it will translate to going from this point on the internet to that point, going up the stack, being an application again, and then going down to the next hop. And if you're a networking guy, you say, this is crazy, it's never going to work. And plus, what about all of the overhead associated with here? So this is, some people thought that it can work. And in the late 90s, early 2000s, when people hit the barrier of the 1%, you cannot improve more than 1%, working very hard, some people said, okay, let's move into that overlay world. And you see a lot of work here that I cite you from this period. And really what is mutual to all of them, each of them tried to solve one specific problem. So they built one specific way to solve that one specific problem. And we were among them. So we had the problem of how do you do group communication and how you scale it. And our 97 spread, the spread toolkit, the first wide area group communication, we released it. We wrote about it in 98. It was too revolutionary, so we couldn't get in. And by 2000, the world caught up. It got in. And then Jonathan had to give the talk, and he was almost decimated. And some people here remember that. You should never do things like that. And then I think all my students that were in that talk were so scared that since that time, every one of them giving a talk in a conference was absolutely prepared, because otherwise they would be decimated. So then we were asking ourselves, so we have this overlay approach that we apply for group communication, to replicate databases, things like that. Why not anything? Why not apply this approach to anything you need, to anything you want to do? And we thought you can. And I'm going to describe today a three-step approach that, each of them was instigated by a challenge and a response to that got us to where we are today. And the first challenge basically came from DARPA. The next challenge came from Stuart Booth from Siemens. And the third challenge came from Malik Khan and Yusuf Javadi from Lifetime. And I'm just going to go through each of them, trying to give you, try to cover both the people who are networking guys and the people who are just came here to honor. To try to learn something from this talk. So, and then I'll touch a little bit about where we are today, what are the challenges ahead. So what was the DARPA challenge? In the 99s, 2000s, 2003, they saw the same phenomenon, but they had a bigger problem. Their problem was they wanted to take the internet technology and use it in their network, right? I mean, they funded it in the beginning, and it doesn't work. you take it to radio networks, networks that don't work that way, and everything collapses. It just doesn't work. So the challenge was, can you take the traditional applications and make them work on networks that have not so good connectivity? That was the DARPA challenge. Now, from our perspective, the challenge was, can you take the emerging applications and make them work on the traditional, the typical connectivity, the internet? And apparently, those two challenges were the same. They were really the same. And I want to give you an insight of why it happens. So I'm taking one point here, end-to-end reliability. Let's say we are here in Baltimore, and we are interacting with our Wells Fargo bank that just took over our bank, that took over a previous bank, that took over a small bank that we wanted to be in when we came to Baltimore. And it sits someplace in California, right? So if I want to access it, it needs to go all the way from Baltimore to California. And if you want to do it on networks, end-to-end nodes, it's about 50 millisecond give or take to do one way. And then to get the response, another 50 millisecond on the other side. So let's say we're starting to send messages, downloading some file or picture, all of them, they love to give you big pictures. And so they start to flow. First message, second message, third message, all of them make it. Fourth message, the fifth message goes down. You lose it. Okay, you're happy. Up until you get the sixth message. Uh-oh, I missed the fifth message. Can I get it back? Okay, give it to me back. No problem, here it is, because the recovery, the brain is at the end. It's not in the middle. So then you get it back, and then you can deliver 5 and 6. So you need to deliver it in order. Why is that? You have a picture, and it's broken into small pieces to pass it through the network. Now, to build the picture again, you need the pieces in the same order that they were broken, otherwise it'll be gibberish. So that's why 6 has to wait, and 7, and 8, and 9, up until 5 comes finally, and then you can deliver them. Can we do better? So a lot of people said, yeah, we can improve how that protocol works in the end. And we said, well, we can just put some nodes in Phoenix, Dallas, Atlanta, DC, and then play the same game. Okay? Now, how would that game look like? That would be hop-by-hop reliability. And here there would be regular computers running regular software only in a few places, and they will keep track of what's going on. And let's see what happens there. So 1, 2, 3, 4 pass. 5 is lost. Where is it lost? Between Dallas and Atlanta. Okay, so 6 comes to Atlanta. Once it reaches Atlanta, Atlanta says, well, I lost 5. Give it to me. Meanwhile, 6 is continuing its flow, and then Dallas can recover it, and then they can be delivered. How much time do you take? 20 milliseconds. Okay, if each of these is about 10 milliseconds, to recover that only took 20, not 100. Okay, so it's much, much better. Especially if you think how many packets are waiting at the end before you have to deliver it. So if you just wait a little bit, you see a stream flowing with no problem. Okay, what does it mean technically? What we have here is a graph. It shows for a 50 millisecond network, what do you get, what is the average delay, the average latency for reliable communication as the loss rate changes, okay? If everything works, and usually everything works on the internet, you are here at 0, and both of them show about 50 milliseconds. As the loss start to go up, and that happens on the internet, by 0.5% you start to see problems. By 1%, now you're almost paying twice. By 1.5%, you're paying 3 times. By 2%, you have no communication. 2%, you have no communication for coast-to-coast. So What happens with the overlay is the red line. You barely notice it, on average. So I stress that it's on average. So there's another factor. What is the variance between packet to the next packet to the next packet? Either you want it to be smooth. If you use the internet the way it is, you have a lot of jitter. There's a big variance between how much time it takes this packet and the next packet and the next packet. If you look at the overlay, the variance is pretty smooth. It doesn't almost exist. So this is a simulation. We implemented it and run the implementation on emulation, and we see more or less the same phenomena. Now, a very interesting question here is, how dense does the overlay need to be? How many of them do you need between California and Baltimore? That's a key question. If you need 100 of them, who's going to put them? Okay? If you need only one, then you don't need it. So this shows, the red line shows what happens if you want to work on conditions of 2% loss. And the blue one, what happens if you want to work on condition of 1% loss. And we see that more or less by 4 hops, we really captured most of that effect of using an overlay. So what does it mean? 12.5 milliseconds, 10 milliseconds. So we say, okay, 10 is round. Put an overlay node 10 milliseconds away, and you have it. Now you can calculate how many of them you need to cover the globe. Okay? I'll leave it to you as an exercise. Now, these are great ideas. Here is where the situation is different in my group. Okay? So you have a great idea, and you can simulate it. What do you do next? You published about it. Okay, what's next? We actually build it. Okay? But we don't build it so that we can test it. We build it so that it can drive the world after that. Okay? And that's the unique aspects of the people that come to a group like that. So we built spines as an overlay messaging, just a router, and made it available as open source. And I just want to give like 2 minutes, what does it mean? Basically what we have is a code software that has 3 components to it. There's one component, the top one, that talks with the clients, with the regular applications. The regular application thinks they talk with the internet, but they don't. They really talk with spines. Spines talks with the net. They don't know that. The middle is really your overlay route. Is the software route. So you write routing code that knows what it's doing and has way more information than a regular router can, because it deals with a much smaller network in terms of the number of participants. And then in the lower level, every block like that is a specific need of an application. So the reliable hop by hop is one block like that. You want to do like internet on this architecture is another block. You want to do audio is another block. This is like a 2007 kind of that. So it also covered the next that I'm going to talk about. You want to do TV, turns out you need another one. So all of these combined, how big is it? It's between 10,000 and 20,000 lines, period.